Okay, so first let me talk about the test, and then I'll answer any questions you have related to test stuff, um, including if anyone has any questions about the extra problems that we did in lab. Those are, uh, the problems on the exam are going to be more like the assigned questions, less like the ones on the lab. But if you're curious about any of those, okay. So exam 2, not with the answers, but the labs are up there. Yeah. Um, so the topics. Um, that's everything up through. There's always a lot of talking over on this side. It's really hard when you're talking right in my face. Okay, so everything up through particle kinematics and 2D. And these are cumulative exams, so you probably want to go back and glance at uh, the old questions and make sure you remember that stuff. I think one strategy that I think works pretty well is if you go back over the old questions. I mean, assuming you don't want to do every, excuse me, you don't want to go through every question again. You don't have time for that. But look over the questions and just ask yourself, do I remember where I go from this? I see this. Do I know where to go? If like instantly you're like, blah, 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 then you're probably good on that. No reason to work through that. Wait until you hit some where you're sort of shaky on them and then spend a little time reminding yourself how to do the questions like that. Okay. Um, so anybody have any homework questions? Number 6, sure. In 2D kinematics? Okay. Anybody have, do I have that? Yes, I do. So 2D kinematics. And I'm not writing particles, but everything is particles. Um, okay, number 6. So a ball is thrown into the air from a starting height h and reaches a high point of h max. That one? Okay. So a ball starts at height h, reaches the highest point of h max. Um, and we want to figure out the initial speed of the ball. Um, it's not the basketball one. I'm talking about the basketball. What? I'm talking about the basketball. Yeah. What about it? Is this it? No, I'm just wondering, like, is it like 60 degrees above horizontal? I think we're talking about a different. We're talking about two different problems. Oh, this is 6 on 2D. I'm sorry. Yeah, this is the basketball one. Sorry. No, sorry. I was looking at the wrong set. Okay, so basketball. So we know that um, the initial direction is 60 degrees above horizontal. And from there, it's going to follow a parabolic path. And um, we know the height of the basket. And I think it gives all these in feet. Um, but 15 feet is, so 3 point what? That's the height, right? 3.05. And then this distance is at 4.57, I think I remember, meters, 15 feet. Um, and we know that it has an initial speed of 7.8 meters per second. That speed is not going to be constant. Things in free fall are always slowing down as they're going up and speeding up as they're coming down. Um, but we can figure out the initial velocity with that. Uh, and we want to figure out, assuming the shot is made, what's the height that it's shot from. It's 15 feet, and I think that's what you get in meters. Um, so we're going to figure out the height that it's shot from. And then the displacement vector. So the displacement vector from the shot location, where it's shot from, uh, to where it is at its highest point. Okay, so we have to figure out what variables we know values for. Before we can assign values for any of these things, we have to choose a time equals 0 instant and a coordinate system. I'm going to do what I normally do and just put the origin of the coordinate system on the ground beneath where it is at time equals 0. And time equals 0 is going to be that instant where it's shot. Okay, so and then also to do calculations involving an instant t, we have to specify what instant time t corresponds to. First, we want time t to be when it gets to the basket. So this is going to represent our time t. Do we know the elapsed time, like a stopwatch time for when it gets to the basket? No. We do know the acceleration vector is 0, negative 9.81. Do we know the position at time equals 0? Yeah. And the way I put the coordinate system, it's a 0x component, and yeah, y is unknown. That's what we're trying to find. I guess I'll call it maybe h0 or something. So I'll call this 0 for x, h0 for y, and this is what we're looking for. Put these two close together. Do we know anything about the position at time t? Yes, we know everything about it, in fact, and that's kind of unusual, but that's how it is in this problem. The x position is 4.57, if I'm remembering that number right, and the y position is 3.05. Do we know anything about the initial velocity? Yeah, and we can get that from So if I draw the coordinate system, we know that the initial velocity vector is oriented like this, and it has a magnitude of 7.8. And it makes an angle of 60 degrees above the horizontal. And so that initial velocity vector is 7.8 times cosine of 60, 7.8 times sine of 60. I guess the y component is going to be 3.9. The x component, can someone calculate that? 6.75. Okay, so the initial velocity is 60. Thank you. Yep. 3.9, 6.75. Okay, so that's the initial velocity. And then, do we know anything about the final velocity? We don't know the y component because that's changing all the time because there's a y component of acceleration. We do, like at cocktail parties, we can bring up the fact that the x component is going to stay 3.9 the whole time, but we're not going to use that in our calculations. If you're under 21, don't go to cocktail parties yet. Okay, so is there an equation that has h0 in it and everything else in it is known? Mm-hmm. Okay, so yeah, if there's no equation that works for this, then the way we're going to go is find time. And I think you're right that nothing's going to work. So our plan B is to find an equation that lets us solve for t, and then we'll try to plug that into something to help us get h sub 0. So the equation that should work is px is equal to p0x plus v0xt plus 1/2 ax t squared. So this says 4.57 is equal to 0 plus 3.9 t plus ax is 0, so this term is 0. And so t is equal to 4.57 divided by 3.9. So what do you get for that? 1/7? Okay. So now that we also have a value for t, the stopwatch time of the flight, is there an equation that'll let us solve for h0? And what you see most of the time, most often, is if you use the position equation to solve for t, then you use the position equation, just the other component, to solve for what you're trying to find. And I think that's what's going to work here. So now we're going to use py is equal to p0y plus v0y times t plus 1/2 ay t squared. And so that says 3.05 is equal to this thing we're trying to find, h0, plus 6.75 times 1.17 minus 4.905 times 1.17 squared. And then just solve for h sub 0. And I think the answer to this is kind of like makes it seem like this isn't the best strategy for shooting free throws. I think you come up with something that's like 5 meters, right? Like you got to be pretty tall for this to work for you. Um, but can someone calculate that? What do you get for h sub 0? 5.2 or something? What? Oh, really? Oh, that's not bad. Oh, 1.8. Okay, that's reasonable. We don't know what the final speed in the final y component of velocity is. That's right. If you're looking for the highest point, then that's true. The y component is 0. But the basket isn't the highest point. You know, what's happening here is something like what's drawn there. The highest point in the flight is going to be here, you know, somewhere above that. Any other questions about that part? Number 6 on 2D kinematics. Okay, and now we'll go to part B. And this asks us something about the highest point in the flight. And so we're not going to be using the same time t that we were for part A. So now this time t is the instant that the ball reaches its highest point. And so let's think again about, we'll keep all the rest of the stuff the same. Time equals 0 is when it's shot. Coordinate system stays in the same place. And now we'll think about, again, which of these variables we know values for. So t, a, p0, p, v0, and v. Time t, now we solved it for part A, but it's a new value now, so we don't know what that is. The acceleration is still 0, negative 9.81. The starting position, the position when time is equal to 0, we calculated that in A, and so we can use those values. We still have 0 for x, and now we know we have 1.8. The final position, we don't know anything about that. And, excuse me, v sub 0, we know, we calculated that. That is 3.9, 6.75. And then the final velocity, well, in this case, there is something about the final velocity that we have to use. We know that the y component of velocity at time t is 0. We don't know Vx. And we're trying to calculate the displacement from the incident shot to its location at the highest point. That means we have to figure out the full position vector at time t, and then subtract the initial position vector to get the displacement. That's the definition of displacement. We're looking for this whole thing. Okay, is there any equation that works? Well, you know, we're going to have to do 2 different steps because we're looking for 2 different components. We could use the y component of the We could use the y component of this. But then we wouldn't be able to go anywhere to get the x component without solving for t first. So I'm just going to solve for t first and then plug it into each of the two position equations one by one. That would work, and if you want to go that way, there's not really any reason not to do this. But I'm going to use this. Vy is equal to V0y plus AYT. So Vy is 0. V0y is 6.75. AY is 9.81 times t. And so the time to reach the highest point is 6.75 divided by 9.81. And what do you get for that? .69 seconds. Does it make sense that does that sound reasonable compared to the other values we have? Yeah, to hit the basket, it took 1.17. This was a little more than halfway through the flight, so that seems about right. And now we can plug it in one by one to these two position equations. So Px is equal to P0x plus V0x times T, 1/2 AX T squared. So Px is equal to 0 plus 3.9 times 0.69 plus 0. And what do you get for that? .69 meters. So a little farther than halfway along the path, along the horizontal path. So that makes sense. And then for the y component, question? Py is equal to the initial value of Py. Well, I'll write out the equation. Okay, so Py is what we're trying to find. And that's equal to 1.8 plus 6.75 times 0.69 minus 4.905 times 0.69 squared. And what do you get for Py? 4.126. Okay, so at its highest point, it's about 1 meter higher than the basket, 3 feet higher than the basket. And then it falls down to where the basket is. So now we can put these together into a single vector, and the position at the highest point is 2.69 for x, 4.13 for y. And then the problem asks about the displacement vector. Isn't that what we got? We just calculated that first, so yeah. Okay, so the displacement is the position at time t. minus the position when the ball is shot. That's 0x 1.8y. And so you get a vector, a displacement vector of 2.69 for the x component and 1.3, 2.3 for the y component. Okay, so let's think about what that vector looks like. Our coordinate system's like this. So we're talking about a vector that's a little more horizontal than it is vertical. Maybe something like that. Okay. And what does that vector represent? That represents a vector going from the starting point that we're considering. For us, that's this, to the final point that we're considering. That's the highest point. And so this is the displacement vector that we just calculated. Okay. And if I had asked for the displacement vector that goes from the starting point to the basket, that vector would be from here to the basket, so it would be a little more horizontal and a little less steep. Any other questions about that one? Any other homework questions? Yes. Sure. Yes. Okay, so a person is capable of swimming 4.5 miles per hour across a 0.15 mile wide river. So a person can swim 4.5 miles per hour. And the way you want to think about this is a person swimming is capable of generating a certain velocity relative to the water that they're in. So if you're in a pool, you're really going compared to the ground 4.5 miles per hour. If you're swimming opposite a current that's going 4.5 miles per hour, the opposite way, then you just stay in place. And that's how, those swimming pools that everybody in Edina, I assume, has, where they're like this long and you just swim in place, So the idea is you're still swimming 4.5 miles per hour relative to the water, but the water's moving the other direction. Okay, so now we have this river that's 0.15 miles wide. Yeah, sure. Yep. I think you can also, everything here is in miles and hours, so you can also just leave it as it is, but it's not like it wastes much time or anything to convert it. The river current has a speed of 8 miles per hour. Okay, so the water's going this way. And the person is going to swim straight this direction. And so what's going to happen is the person is going to be going that way while the river carries the person downstream. And the question is, that's a really fast river. You probably want to just walk around and look for a bridge. Yeah. partial credit for that. And so this is a relative motion problem, and we want to set it up like the velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water plus the velocity of the water relative to the ground. And we have to choose a coordinate system, so we'll choose X like that, Y like that, and you can choose any, any directions you want. But so now we want to calculate the velocity of the swimmer relative to the ground. And that's equal to the velocity of the swimmer relative to the water. Now, relative to the water, what the swimmer is going to be doing is swimming straight this way and at a speed of 4.5 miles per hour. So that's in the positive y direction, so 0, 4.5. And the water relative to the ground is the velocity of the current. That's going straight in the positive x direction the way I drew it. So that's 8, 0. And so somebody with a speed gun measuring this swimmer, so if somebody's standing on the shore measuring the velocity of the swimmer, they're going to see the swimmer moving at 8 miles per hour in the x component and 4.5 miles per hour in the y component. Okay, so now we can think of that as the velocity vector, and this person's moving with a constant velocity. So what's the acceleration going to be? That's right. So the acceleration is 0, 0. And now we're trying to figure out kind of what the x component of the position is going to be when this person reaches the other shore. So now we're on a constant acceleration problem. The acceleration 0, that's still constant, so we can use these equations. So let's think about what variables we know and what variables we want. Okay, do we know the time it takes to get across the river? No, we just figured out the acceleration is 0 because it's constant velocity. Do we know the starting position? Yeah, that's where I drew the coordinate system. That's 0, 0. Do we know anything about the final position? We know one thing about it. We know why, because we know he gets across the river. Okay, we just don't know how far downriver he lands. So we'll leave this as P0x and then 0.15. This is what we're trying to find, is this P0x. And then the initial velocity, that's what we figured out in the relative motion problem. So that's 8, 4.5. There's no constant acceleration equation that'll let us solve this by itself. There, no equation works. So we're going to find t. And we're going to do that using the equation that says py is equal to p0y plus v0yt plus 1/2 ayt squared py, that's 0.15, is equal to 0 plus 4.5 t. And so t is equal to Is that exactly 30 seconds? Oh, we're doing this all in hours. Okay, so that's point 0.03 seconds. Minute. Guess was right. Okay, and now we can plug that into px is equal to p0x plus v0xt plus 1/2 ax t squared. And so px is equal to 0 plus 8 times 0.03 plus 0, and that is 0.24 miles, right? If you kept, so okay, if you didn't round this, 3 times 8 is 24, right? I'll write it like that. Any other questions about that one? All right. We have a quick